start. It is our pleasure to have here today Carlos Antón Solanas. Normally in this kind of lectures on material science, we bring people from abroad, but today we have someone very close to us because he's working in the campus. So Carlos made his doctoral thesis at the Autónoma University, Madrid, in 2015, under the supervision of Luis Viña. Then he moves to France, to the CNRS for the first postdoc, till 2019, under the supervision of Pascal Senecar, and then moves to Germany, to the University of Oldenburg, till 2022. From this moment, he's back in Madrid, in the Department of Física de Materiales of the Autonomous University in Madrid, and he's working with a Talento, attraction of Talento program. And today he's going to tell us about the quantum optics with solid-state sources. So thank you, Carlos, for coming, and the floor is yours.
Thank you very much for the introduction, and also thank you very much for the invitation to give the lecture. It's a real pleasure, a real honor to be here today and have the chance to present a palette of results that I have been recently obtaining. So today I will be discussing about quantum optics with the solid-state materials. I tried to compile results from the last 5 years in the most coherent possible way, and also attending to the requirements of the direction board that invited me to be here. So I try to keep everything understandable or as much as possible, but if there is something that is not really going, you can stop me and ask, and I will try to do my best to clarify anything. Architecture around applications with quantum optics, we can think of, well, first of all, I will organize the talk with the introduction to solid-state single photon sources. I will try to give what is the benchmark for an ideal single photon source, and I will also indicate what is the current state of the art for the best single photon sources, what kind of applications are reachable at the moment, and where are certain companies competing for in order to even break the new barriers of the state of the art. Then I will be focusing on experiments that I've done with single photons in different types of materials, semiconductor quantum dots in transition metal, decalcogenides, monolayers, and also more recently on HBN defects. And if I have time, probably I will not. I will discuss about other experiments that I'm doing at the moment involving many photons. These are results from exciton polaritons in different materials, perovskites, and also in gallium arsenide quantum wells. I say they are Raúl. There will be some results. Maybe I'm presenting as well. Well, if I just get to number 2, that would be fine. So, as I was saying, the generation of pure states of single photons is a resource for developing these 3 axes of quantum technologies: communications, computation, sensing, and metrology. As one would imagine, communications is using single photons for communications is the natural way to proceed, because single photons propagate for long distances without interacting with environments, and so keeping the information that they are carrying. I will discuss as well some advancements that there are at the moment on quantum computation using photons, although it is pretty challenging, and they have to compete against platforms that are quite advanced, as it is superconducting qubits and also arrays of atoms. And then finally, I will give as well some results that I obtained recently that are aiming towards sensing and metrology. As you maybe imagine, single photons are also, or quantum light in general, is very useful for this branch of quantum technologies. If you think of the detection of gravitational waves in LIGO and Virgo and LIGO, they are using squeeze states that allow you to detect changes of very, very small sizes in the interferometric arms of these gigantic Michelson interferometers, right? So, keeping in mind for what it can be useful, these single photons, let's try to define what do we understand as an ideal single photon source. And you can imagine that you have a single photon gun that is launching single photon states, and then the 2 main benchmarks that you will be paying attention to is on one side the brightness, and this is if I pull the trigger whether I'm gonna get a single photon or not, with which probability I'm gonna obtain that single photon, and this is called brightness, and it can be defined in different parts of your setup depending on where you are interested about of characterizing this brightness. It is pretty complicated to indeed obtain a material that is going to deterministically generate that single photon as you like. I will go to that later. And then, very, very importantly, the next important property is the indistinguishability, which basically is telling us whether those single photons that are emitted, they are identical in all possible degrees of freedom. So I want that single photon to be identical to others in energy, time, polarization, spatial distribution, orbital angular momentum, or any other degrees of freedom that you could imagine. The way to measure it, I'm highlighting it here, for those that you may not know, is done via the Ongo-Mandel interference, where you send two single photons to a beam splitter, to the input ports of a beam splitter. If they are fully identical in all the degrees of freedom, this bosonic coalescence will make these two photons exit the interferometer, the beam splitter through the same port, bunching together. So this is basically the experiment that allows us to determine how indistinguishable the photons are. And by far, is one of the most complicated properties to control, especially in the solid state. Okay, so I would like to start paying attention to what is the state of the art at the moment on the generation of single photons. And historically, we have to first mention the probabilistic or heralded single photon sources, where we can identify two types. This is spontaneous parametric down conversion, where you are pumping your crystal with a given laser wavelength, and then you will obtain two photons, signal and idler. And what you do is to use the heralding of the idler photon in order to herald the presence of another single photon in the other mode. For wave mixing, similarly, it is using, in this case, a Chi3 material. And again, from two photons, you will generate, in general, two photons of different colors. And you can herald one and then know the presence of the other. The main problem that this technology presents is that the quantum state that you are generating is an infinite superposition of n photons, pairs of photons in the idler and the signal modes. Meaning that if I pump harder my crystal, I will start to generate multi-photon order pairs, and so this will not be anymore a single photon source, but a single photon source that contains multi-photon noise and that kills generally all your quantum applications. So this means in turn that if we want to get only these two terms here, the 00 plus 1, and I'm using the one in the idler to herald, if I try to make it brighter, this is going to be at the compromise of increasing the multi-photon noise. So you can see here this G2 experiment that tells you how much multi-photon noise you have, and you see that the harder I pump my glass, the brighter I make it, the worse it is this G2, meaning that I'm increasing the multi-photon noise. And of course, at the same time, if I'm testing the indistinguishability as a function of the brightness, you will see as well that this indistinguishability decreases. So you have a bound between the brightness that you can get and the indistinguishability of your single photons. And the idea is to check a different type of technology in which this bound is free. You can have a brightness of 1 and an indistinguishability of 100% as well. Okay. In order to address this question, we turn our attention to what we call, or what we like to call, deterministic sources that are basically natural atoms or artificial atoms that emit single photons via the spontaneous emission. I am just indicating here below what are the two parameters that solid-state physicists we are paying attention to when we have to choose our desired solid-state material to emit single photons. The first important one is the quantum efficiency of the emitter. This means if I have generated my electric state excited and it has to recombine, I want to have this recombination through a radiative channel and never through a non-radiative channel, because this is going to kill my brightness, right? And the other important feature is the Debye-Wohler factor, which tells us how much our atom or our electronic transition is interacting with the system and may exchange phonons, vibrations with the system, broadening my spectrum and decreasing the quality of my single photon emission, so worsening the indistinguishability. What I am plotting here is a graph that I like very much from this review paper, where they are trying to represent the product of the Debye-Waller factor and the quantum efficiency versus the lifetime of different types of emitters in the solid state. You can see already that semiconductor quantum dots, they are very much at the top. You can see also defects in HBM, they are doing pretty well. And you can see at the same time that silicon vacancies in diamond or NV centers in diamonds, they are pretty low. So the people that are doing, for example, quantum communication protocols with NV centers, I think is pretty challenging because they are very good for other applications such as metrology or magnetometry. But for the sake of emitting efficiently single photons, there are probably other sources, other materials that are offering better scalability or better properties. Okay. Then the next thing that is very important in order to make a deterministic single photon source is to make use of cavities, optical cavities, in order to redirect your emission in a given direction, in a given mode, and try to extract that single photon as quick as possible. And this you can do it via cavity quantum electrodynamics, in which what you're basically going to do is to inject or insert your atom, a neutral atom or a solid state material inside of a cavity, and have it interact with the photonic mode that is trapped inside the cavity in order to eject that single photon in a controlled direction that I'm highlighting here, and also with a lifetime that is going to be much quicker, so that my emitter will not have time to dephase with the environment, keeping the indistinguishability as high as possible. So the figure of merit is the parcel factor, which basically tells us how much this atom and the cavity are interacting, divided by the radiative recombination of my atom, and then the quality factor of my cavity, this is kappa, and gamma, which will be the full linewidth of my emitter. And this parcel factor, which you want to be as big as possible, plays a very important role for the final brightness that you get and the final indistinguishability. Okay. So there are many different types of cavity architectures that you can use in the solid state. I am picking up here a review, it's already 10 years old, that considers different types of photonic resonators, such as micropillar cavities, photonic crystal cavities, nanobeam cavity, and microdiscs, with different properties and with different specificities that in the end will get you have better single photons in a given way. I will be discussing results mostly using this geometry from my work and then collaboration with a group of Pascal Saint-Lérard, where we have been mostly using micropillar cavities to parcel accelerate the emission of single photons from quantum dots. Then, if we are looking at the current state of the art for the emission of single photons, we have to be looking at recent papers from the group of Warburton in Basel and from Zhangwei Pan in China, where currently the little quantum star that we have on Earth is composed by semiconductor quantum dots that are coupled to a Fabry-Perot reconfigurable cavity. We like to call this an open cavity, and basically it's just two mirrors that are mechanically controllable one to each other, and where we can parcel enhance the emission making of this device a really, really bright single photon source. I write here the two figures of merits that I was discussing from the very beginning. This is the brightness of detection. Okay, so this is, if I pull my trigger, what is the probability that I will detect that single photon? This parameter here is very punitive, because it considers what is going to be the transmission of your setup and the efficiency of your detector. So I am including it as well, and even so, the chance to detect a single photon is 55%. This is absolutely crazy if you think carefully about it. And then the parameter of the indistinguishability, when I am getting the stream of single photons that are emitted from my device, if I delay them for a delay that amounts 50,000 times the lifetime of that single photon, the indistinguishability that I will measure is on the order of 95%, which is quite great. So basically, this is at the moment what it's the most efficient single photon source, and that is allowing us to make crazier experiments in the field of quantum photonics. What I wanted to say is that with this technology of semiconductor quantum dots coupled to cavities, there are certain benchmarks that allows us to see the importance of these single photon sources. On one side, by the way, all these experiments implemented in China, I must say. On one side, for computation, in 2019, the group of Zhang Wei-Pan demonstrated the boson sampling of 20 input photons in a multimode interferometer with 60 modes, and they were basically characterizing the quantum state at the output. This is important from a computational point of view because given your interferometer, this constitutes some sort of unitary matrix. The capacity for a given input of photons, the capacity to calculate what is going to be the output distribution, this is done via the calculation of permanence. Permanent is the same as like a determinant, but always put in plus when you are doing the computation. And from a computational point of view, the calculation of those permanents is NP hard. So it's really, really complicated. This is why it's interesting to do these experiments with photons, because you just inject your configuration of photons and you don't need to wait ages of the universe to see what is the output. You can see it relatively quicker with this type of experiment. There is also this other experiment about fusion gates. That is a technique in order to do also quantum computation. And then on communications, there are these two implementations. This first one that is testing that you can do a Bell measurement between two sources that are separated by 300 kilometers in fiber. And then this other one that is pretty recent, in which what they have demonstrated is that the communication in a quantum key distribution protocol, in this case I think is a BB84, they are showing that in a certain range of losses in free space, they are capable to communicate the key more efficiently than if you are using decoy states, as it is done generally. Decoy states, it is just simply an attenuated laser. So in this paper, they are basically telling us that for a given amount of loss, the communication of that key, it will be much faster, much more efficient with single photons, just because you don't have these multi-photon components that lasers always carry. Okay, so this is just to tell you that it is not about saying how great your numbers are on single photon emission, it's also how far you can reach on testing different applications in computation or in communication. Okay, and then finally, a slide that I like to include and that I have to change relatively often, it is which other platforms are being investigated at the moment with other materials in order to generate single photons in the telecom range. As you can imagine, this is very interesting for communications because telecom is the suitable wavelength to communicate information through optical fiber. And I would like to mention this implementation with erbium ions that can be coupled to a silicon cavity, and also different research groups that are also working with centers in silicon, especially from the group of Anaïs Dreux and Jean-Michel Gérard in France, and also the group of Simmons in Canada, where they are studying different types of centers with different optical properties in order to maybe eventually do quantum computation and communication with this material. Okay. So far, everything good, Sal? Is there any question or? Okay. After discussing on platforms in the solid state, what I do at least most of the time is to look myself on the mirror, being the mirror of the people doing neutral atoms. Okay, in general, the real natural atom community have been doing experiments for, I would say, 30 years earlier than semiconductor quantum dots. So their advancements are generally greater, and their dynamics is also slower, which allows them to do other things. And this work here from the group of Gerard Rempe in Max Planck Institute in Munich is so far the state of the art for the generation of multi-photon states that are entangled. So using rubidium atoms and applying this protocol that I will not enter to discuss very much in detail, and again, those atoms coupled to a cavity, what they are proving is they are capable to generate this Grimberger-Horn-Zeilinger state of size n, being n here up to size 14. So you can imagine here 14 times r plus 14 times left in a quantum superposition. And what is quite impressive to see as well is how other technologies, the demonstration of other technologies are at the moment comparing to this. So it's pretty humbling to see that atoms are scaling with this trend, having here the coincidence rate of detection of the state versus the photon number, while SPDC or quantum dots, we are still there. You may wonder, how is this possible that I have just told you that quantum dots are such good emitter, but still are not capable to compete with the performance of atoms? And my interpretation is that it's taking us a bit longer to get as good as atom people is on the control of light and the application of protocols and the characterization as they normally do. Okay, so also on this line, something that many people are going behind is to apply gates or fusion gates among these multi-photon entangled states. And this is also another result that is from the group of Rempe, where basically they have some new protocols in order to generate these multi-photon states, make partial measurements, and use that final state in order to make even a larger state. And this is on the lines, applying these fusion gates is basically the idea that was proposed by Roxendorf and Briegel, where this generation of multi-photon states and application of fusion gates will allow you to make computationally hard tasks. Okay, so from here, I would like to discuss at the moment what is the current competence between at the commercial level, so to say, between companies on quantum computing with photons. There is this recent paper from Quandela, where they are trying to compare the performance between their technology, this is semiconductor quantum dots coupled to a micropillar cavity, and the other competing company, PsiQuantum, in the United States, where their core technology is four-wave mixing in silicon circuits. So what is very interesting of this paper is that they are considering as a resource state for their quantum computing scheme this 6-ring state, which is composed by 24 photons, okay? And they consider this from a theoretical standpoint, what it would be required with quantum dots and what it would be required with four-wave mixing in order to get there. So first of all, in this kind of technology, we know that this is heralded single photon emission. You have to detect one photon in order to avert the presence of the other in other mode. And this, it's called deterministic, because you know that every time you excite, you're going to generate that single photon. If you compare the benchmark of the brightness, this is generally on the order up to 5%, and this is, in principle, can be brought up to 100, and this brightness is the one that you characterize here at the level of the source. This is not detection brightness. Regarding the photon quality, if you decrease a lot the brightness, it is well known that the quality of the single photons emitted via four-wave mixing is really, really high. But equal good purity can be also achieved with semiconductor quantum dot sources. And now it comes the very impressive comparative point between the two technologies, and is that if you want to generate this type of highly entangled state with whatever scheme it's required, in this case it would be all photonic fusion scheme, and here it will be repeat until success scheme. What, according to this study, it tells us is that for PsiQuantum you will require 1 million of these sources, and for semiconductor quantum dots you will only require 12 single photon sources that are emitting all the time equally indistinguishable photons. And now the question is, which technology has more chances in order to achieve this benchmark, right? So I think it's a nice example because it's telling you exactly what are the challenges at the moment for this integrated technology and probabilistic technology, and this other technology where in principle you will require less sources, but equally, I would say, that is going to be very hard for the people that we are working on material science to be sure that we will do something very clever on the synthesization of quantum dots or other states in the solid state that will allow us to get reproducible sources emitting always the same type of single photons. I am highlighting here another recent paper from the group of Warburton, where they have demonstrated that with droplet epitaxy semiconductor quantum dots, they can get a really high indistinguishability from two dots that are separated. And this does not require any cavity. This is just the emission from the two interfered, demonstrated that they are really, really indistinguishable. This is one thing. One thing is to have two dots that have the same properties, same lifetime, same spectrum, everything, and that they have a good indistinguishability. Another challenge, I think, is to be able to have a very efficient post-selection system to see which is the best dot, or make something extremely clever at the material science level in order to have single photon sources that are all identical. So I think this is my impression, maybe I'm wrong, but it will take some time, I guess, to get there, to get to this benchmark of 12 sources being producing single photons that are absolutely identical. Okay, so this was the introduction so far for solid-state single photon sources, comparison with atoms, with heralded technologies, and what is at the moment the most amazing implementations for communications and computation. And now I would like to jump into the experiments that I have been doing over the last years, both in self-assembled semiconductor quantum dots, and then also in emitters in monolayers of TMDs, and also defects in HBN. So for this first part, where I'm going to be discussing results on semiconductor quantum dots, I would like to start to motivate this research about the different ways that you have to encode information in light. You have many different options: this path, energy, time, polarization, even orbital angular momentum. But at the time when I was doing these experiments in 2019, we started to explore a different way of encoding, that is to encode in the photon number basis. Okay, so you can think of now trying to make a quantum state of light in which you are using vacuum, 1 photon, 2 photons, 3 photons, and then use different types of superposition and entanglement in this base in order to think about applications. So the first question that we had at the very beginning was whether we can make just a superposition state of 0 and 1 photon. Then the next question that we try to address is from superposition we can jump into the simplest type of bipartite entanglement that we did in this case in time. And then from there I will discuss some theory results and also partially experimental results where we can scale this complexity in entanglement in order to have photon number encoded states entangled in energy and time. I will try to accompany all these results with some applications that we thought that could be feasible on the way. And yeah, basically one of the motivations to harness this degree of freedom is that it's an infinite base. So in principle you can have multidimensional states, because the focus state can be as large as you can. Okay, so first of all I would like to discuss what type of atom we are having with these semiconductor quantum dots. We are going to be using positively charged excitons, which has this 4-level system that you can see here. You have a resident hole that can be spin up or spin down, and when you bring it to the excited state, you have a positively charged exciton of these two kinds. If the magnetic field is 0, these two energy levels are degenerated, and the transitions that they follow is sigma plus along this direction and sigma minus along this other, or if you rewrite it in the linear basis, you can decay with vertical polarized light or horizontal. In order to resonantly drive this transition, what we do is to implement a cross-polarization excitation scheme where we have resonant pulses of laser light. We choose the V polarization in order to drive the transitions, and then with a polarizing beam splitter, we choose horizontal, which will be half of the light of single photons that have been emitted in the orthogonal direction. And if you think about it, even though what I'm going to tell you is not really true, this 4-level system, when I'm doing resonance fluorescence in cross-polarization, it can be simplified to an effective 2-level system. So everything that I'm going to be describing today, you can think of just an excited and a ground state that is driven with a resonant laser. Just to give you an idea of the type of lifetime that we are having, if you're in-gas semiconductor quantum dots emits in free space, this is going to be a lifetime of the order of 1 or 2 nanoseconds. In the micropillar cavity that we are using, the emission is partially enhanced with a factor of 8, which leads to a lifetime of on the order of 130 picoseconds. Okay, so for the generation of superposition and entanglement in the photon number basis, what we are going to be harnessing as a motor of entanglement, it is simply the spontaneous emission. Okay, so what is happening during the spontaneous emission is that you first initially bring your two-level system to the excited state. I am writing here the amount of light that is emitted. So in this first case, you are just having your quantum dot in the excited state and emitting vacuum. And while spontaneous emission is happening, you can have a superposition between the state of your atom and the state of the light field. So there will be a moment during the spontaneous emission in which you are having a superposition of these two states, excited vacuum plus ground, 1 photon, until you have the total decay where your state is this one. Following this same reasoning, in order to generate superposition in light, the only thing that you have to do is to prepare your atom in a superposition state, that this we do with a resonant pulse that drives you below pi pulse. So what you will be doing is to prepare just a superposition of ground and excited states with these two coefficients, alpha and beta, that you can deterministically control just by changing the power of your laser. And if you have not completed to bring your atom to the excited state fully, and you are starting from this point, when you wait for the total spontaneous emission to happen, what you will find in the photonic mode is that this superposition that you had initially in the atom is brought to the light field. So this is just the simple idea behind to generate a superposition of vacuum and single photon. The way we realized back in those days, in order to check that indeed we were generating this state, is with interferometric means. So we were generating this quantum state of light that I'm representing here with this density matrix, which is a subspace of vacuum and single photon. And by injecting it in this path unbalanced Mach-Zehnder interferometer and re-interfering them back again in this beam splitter, we could see that the intensity clicks between the two detectors was oscillating freely because of the vibrations of the two mirrors in the scale of a few seconds or even lower. And the amplitude of this visibility, which is intensity in 3 minus intensity in 4 divided by the addition, this visibility amplitude is telling us what is the percentage of vacuum that we are having in the population of vacuum that we are having in the state. And the funny thing is that this quantity is insensitive to losses. You can put here as many filters as you like, that if the losses in these two arms is the same, it still tells you what kind of quantum state was emitted at the level of the source. Okay. One curious thing about this superposition state is that the group of Fabio Serrino in La Sapienza, they have used this scheme in order to prove quantum teleportation. Instead of using a quantum state that is encoded in polarization, they are using a quantum state that is encoded in a superposition of 0+1 state, which is the probe beam that you see here. You see that this scheme is exactly the same as the one that was used back in the days by Zeilinger in order to prove for the first time the quantum teleportation protocol. Then the entangled state that they generate here is a Bell state that is encoded in space. So they send a single photon here that is divided in these two paths, making this 1, 0 plus 0, 1. And then it comes the teleportation analyzer that tells you that effectively you have teleported these two coefficients to this mode here. So it was very funny to see this result, that somebody managed to make something useful out of this superposition state. Okay, the next step for us was to try to demonstrate the generation of entanglement. And in order to do that, what we do is to apply a very simple protocol. It's one of the simplest protocols that you can imagine. You are first driving your quantum dot with a pi pulse, so you bring your two-level system to the excited state. Then you wait for a certain amount of time before the spontaneous emission is fully completed. Then you apply a second pi pulse that rotates the state of the atom, and then you wait for the full decay of your emission, leading to a quantum state that is alpha 00 plus beta 11, being 211 the late and early beams in which you can have these two photons. Trying to explain this in a bit more of detail, the resulting wave packet that is emitted from this protocol it looks like that, so to say. So first you have this first pi pulse, you start to decay, and then after waiting a certain time, you come with another second pi pulse that turns the state of the atom, and then you have this other tail of emission. And this quantum state is telling you that if you didn't emit anything yet in the first time being, you will not emit another photon in the second, and vice versa. If you have emitted a single photon here, then you will emit another photon afterwards. This is the kind of entanglement that you are having in this state. Because I didn't want to go very much into the experimental details, the techniques that we used in order to characterize the density matrix of this state was again by self-homodyne detection, so self-interference of these states in an interferometer, and also second-order correlation functions in order to characterize the population of the 1-1 state. And what we could do is to partially reconstruct the density matrix of the state and impose some bounds, but it was not a full density matrix tomography of the state, because in general it's very difficult to work and to characterize photon number encoded states. When you have vacuum in one mode, it is not evident to understand what is the component of vacuum, so you always are obliged to make other type of measurements that will help you to hint what is the component of vacuum and what is the coherence with other modes. Okay. Something funny about these experiments is the generation of multipartite entanglement, something that we like to call at the time Fibonacci states. And is that what I explained so far is the mechanism when you are just using 2 pi pulses, but you can use n. And the recursive excitation with n pi pulses over your state is going to make a very complicated multipartite entangled state in time again. So for example, I'm just highlighting here what happens for 10 pi pulses, where you are defining 10 temporal modes, which is the time between the different pulses. And this leads to Fibonacci state that is composed by these 89 kets, and that at the moment we thought we didn't try to do it experimentally yet, but we believe that maybe it could have some utility. Okay, so something that I did recently, although it didn't work, was to try to use this Fibonacci state at the input of a Mach-Zehnder interferometer to try to see what is the sensibility of phase changes in this interferometer when injecting these states. And without getting too much into the details, what we can see is that the metrological relevance of Fibonacci states in order to determine the phase in this type of scheme is even worse than using a laser. So this limit that you see here is the standard quantum limit. It will be the accuracy that we will obtain in determination of phase fluctuations that goes with 1 over square root of n. And this will be if we are using Nunn states, that is the highly entangled state that gives you the best sensitivity that scales with 1 over n, and this will be the result for Fibonacci states. And it's just recently that I got aware that there is this recent work from Raoul Trivedi from the Max Planck, where he's basically saying that you cannot get metrologically advantage from quantum states of light that are emitted from a two-level system. So this is our case. So it makes total sense that this state in the end is not metrologically relevant. Another thing that I want to go a bit quicker about it is that if you want to use metrologically relevant quantum states of light, there is this proposal from Alejandro González Tudela and Cirac, where they are proposing to use super radiant pulses of light that can be emitted by atoms coupled to a waveguide or atoms within a cavity, where you have a burst of single photons making this type of quantum state in which the scaling of the phase determination it can be as good as the Heisenberg limit. Some of the ideas that I would like to develop in order to make super radiant states in the solid state, it would be basically to try to harness hybrid cavities. So you can imagine here a monolayer material or an HBN sheet that is coupled to each red dot here would be a defect in HBN that you are coupling to a plasmonic cavity, and then everything again at the same time coupled to a Fabry-Perot cavity. The combination of these two cavity modes, plasmonic and dielectric, this will be the dielectric in the open cavity, might generate in the end a burst of single photons with an n scaling with as many defects you can inject here. It's just an idea, but maybe a bit complicated to implement in the solid state. Okay, and then finally, and I think I should start thinking about finishing because otherwise it's going to be too long. I would like to comment on some other recent results that I obtained in collaboration with the groups of Anna Predojevic in Stockholm, Armando Rastelli in Linz, and Tobias Heindel in the Technical University of Berlin, where in order to generate this high-dimensional entanglement in the photon number basis, in this case we have used the bi-exciton-exciton cascade, which is described by this type of decay scheme. For implementing this scheme, we have chosen one of the cascades, okay, simply by choosing with a linear polarizer what is the cascade that we are going to use, either H or V. And by doing so, we make this ladder level become just a three-level system, where we are having the bi-exciton level, the exciton level, and the ground state. In order to rationally drive this three-level system, what we are doing is to use the two-photon excitation scheme, where the laser is put in between the bi-exciton and the exciton lines, and this allows us to directly pump from the ground state directly to the bi-exciton level, and from here have the cascade of bi-exciton and exciton photons. You can see here the typical lifetime that you see from this system, where the bi-exciton should be decaying twice slower than the bi-exciton. Okay, and then the next question, and I think the next slide is a bit messy, so you will forgive me for the next slide. Here I'm just trying to explain what is the excitation scheme that we have been using in order to harness this high-dimensional entanglement, and is exactly the same as the one I explained previously before for the two-level system. So in this case, we're going to be driving first with a pi pulse that is loading the bi-exciton in the excited level here. Again, we will let the system spontaneously decay until we are finding ourselves in this situation where we are having a possible triple superposition of the bi-exciton in the excited state. Bi-exciton decays, but the exciton did not decay yet, or everything has decayed down to the ground level. If in this situation we pump again the dot, what we are going to do is to apply a pi rotation in the cases where the bi-exciton is not there. Okay? Otherwise, the laser is extremely off-resonant. And by doing so, applying this rotation and then waiting for the total decay to occur, what we will generate is this entangled state in which zeros and 1 are encoding energy from the exciton or the bi-exciton, and time corresponding to the early bin or the late bin. I will not go into the details of the characterization of this quantum state again, because otherwise it would be too long and probably uninteresting. One of the applications that we thought about this state is to compare its performance against a G8 set state of dimension 4. You think about this state, it has 4 modes, bi-exciton early, exciton early, bi-exciton late, exciton late. And what we wanted to do is to see if Alice is sending this state to Bob, and there is Eve that is still in one of these possible 4 modes. We wanted to see what is going to be the resilience of the state to the mutual information. And what we see is basically that there are some cases for certain bipartitions of the system, of modes of Alice and modes of Bob, that when Eve is still in one of these modes, we are still having a state that is more robust than the behavior of a G8 set state. So there is another question, and is how Bob is going to detect vacuum when it's sent in the state, but this is one of the possible applications that we could have out of this state. Okay. Then very quickly, and this is because I have a collaboration with Fabrice Lossy that is also working in the ICMM. I would like to discuss some recent results obtained in the group of Kai Müller, where I have the chance to give a little help with the homodyne detection. And in this experiment, basically, what we are doing is to resonantly drive a quantum dot generating a continuous stream of single photons. And in this homodyne stage, what we are doing is to interfere the emission from the quantum dot together with the resonant laser that we are using to drive the dot. And if we generate here a destructive interference between these two modes, the laser and the emission from the dot, by controlling the intensity of the laser, what we can do is to control the suppression of certain multiphoton components. So, for example, when we increase the intensity of the laser up to f equal 2, we will see that G2 is anti-bunched, while the other GNs are bunched, and so on when we are increasing f. So there will be a moment in which G3 is 0, and then the other components will be half in this way, etc. Because this experiment was done with a quantum dot that is not coupled to a cavity, the efficiency of the emission, or the brightness, was really, really low. And so the characterization of n-order correlation functions was very complicated, and we could do the study for G2 and G3, still observing that we can pass from the suppression of the photon component of n equal 2, and then the bunching of the other components, and so on. Okay. How much time I still have? Like 5 minutes? Okay. And for the next experiments, probably are even more interesting, I will just try to go very, very quickly. First, I would like to discuss some results on quantum dots in transition metadical cogenerated monolayers, and then present some ongoing results with HBN defects. These are results that have been obtained in collaboration with a group of Christian Schneider, where we engineered a Fabry-Perot cavity that is held in a closed cycle cryostat, an Autodrive 1000, that allows us to have parcel enhancement from the quantum dot emission in wrinkles of WSE2. And we can observe basically the parcel enhancement. When the cavity is in resonance with the dot, we get a high intensity, and we also see a decrease of the lifetime, obtaining a quite high first length brightness, so the probability of finding a photon here, but the indistinguishability is super, super low, that we attribute to probably electron noise around the dot. On HBN defects, and these are results that we are currently obtaining in the Autónoma. Sorry. I think it's moment to finish. Oh, wow. So in these experiments, basically we are using nanocrystals of HBN that have random defects inside that we have not generated by any means. This is commercial powder that was provided and that contains these defects. We have characterized well, first the brightness that you can see that is pretty bad, the detection brightness. If you compare it with the state of the art, we have the typical saturation curve that arises from the non-resonant pumping of a defect. We have also characterized the lifetime of this type of defects. And then finally, we have also double-checked that is indeed single photon emission by measuring the second-order correlation function with continuous wave and also with pulsed excitation. Trying also to understand what is the degree of indistinguishability of these emitters at room temperature, what we have implemented is basically the Michelson interferometry of the single photon emission emitted by these defects that allows us to map what is the total defacing time, capital gamma, of our emitter. And basically, you have to keep in mind that the lifetime was on the order of 2 nanoseconds when we are measuring this T2 star time, which is the pure defacing time of the emitter, is on the order of 300 femtoseconds. Right? You can see how defaced this defect is at room temperature. And there are some other results from the group of, I think it's Kubanek, where they apparently see that certain defects, they are still resilient to phonon coupling at room temperature, but what we can see is that our defects are heavily coupled to phonons because the T2 start time is extremely bad. So some directions to follow. In first place is to make we are working on it, an open cavity at room temperature. the cavity effects are not going to be enough at all in order to make T1 on the order of T2 star. But we have been working a lot on the engineering of this device in order to get a very efficient extraction of single photons that could be used in certain protocols where photon interference is not required. So what you see here is the part of the top mirror where we have craters of dimples where we deposit a DBR. And this little crater allows us to couple the HBN emission that has been deposited as well on a mirror. And by doing so, we know that it's possible to at least redirect the emission more efficiently to the collection direction and then be used in some protocol such as the BB84 or others. We are starting preliminary analysis in order to analyze the different modes that are confined in this Fabry-Perot cavity. And you can see that when we decrease the cavity distance, we start to see confined modes. These vertical lines that you see here are the different SPD modes of the cavity. We are trying to configure our cavity very, very carefully because it could be the case that the full width half maximum of the emitter spectrum is comparable to the cavity mode, and then the cavity mode could be filtering itself the emission of our emitter, what would be very bad to enter the inhibited parcel regime. The colleagues in Bristol, they have been doing some FDTD simulation for us, where they were telling us which is the most efficient design. And currently we have an undergoing nanofabrication in order to make little craters of 3.5 micron with a depth of 350 nanometers that will force us to make the cavity distance even closer, but then we will have some real enhancement in the emission efficiency. In order to get to closer distance in this Fabry-Perot resonator, it's quite challenging. You have to have a very good alignment between the two mirrors. And this is how we started a couple of years ago, where we were having this design in which you're having top and bottom mirrors within a cavity. The bottom mirror, you can move it with an XYZ stage, and then you can move the whole device with an XY motor that you can see here. But after discussing about these problems of approaching the two mirrors with experts in the Autónoma, and this is Julio Gómez, Pablo Ares, and Nacho Orcas, they suggested us to make some sort of tripod that allows us to remove the residual angle and eventually make the cavity distance even shorter, which is crucial to get this better parcel enhancement. So the cavity characterization is currently undergoing, and we hope to get nice results soon. Just to conclude, on the results of self-assembled semiconductor quantum dots, a direction that I would like to go is towards multiphotonics physics, where there are many ideas. Some of the papers are here, where there are very nice physics to explore in either weak or strong coupling regime between the dot and the cavity. Some direction that is very interesting to follow in order to get towards quantum computing, as you saw, is the scalable spin photon entanglement. This is the scheme that is being at the moment studied by certain groups. For quantum dots in TMDs, the main challenge at the moment is the high dephasing rate, especially due probably to electron noise. And another direction where I'm interested at the moment to go towards is to strongly correlated systems of Murray quantum dots. There is just a PhD student that started in our group, and he's going to be studying this type of physics in heterobilayers of WSE2 and MOSE2 in collaboration with the group of Mauro Broton-Sigisbert and Brian Girardot, and hopefully as well with the group here in the future of 2D Foundry. And then finally, for defects in HBN, we like this material because it has a great emission efficiency and dB-Valor factor, even at room temperature. Maybe by some clever material science study, it will allow us to go towards emitter which are identical in all degrees of freedom. And now I was starting the next part of the conference, but I don't have time to go there. So you just let me go very quickly to first announce this school from the Nicolás Cabrera Institute that I'm co-organizing together with Professor Viña. And it would be great if we could have more people joining it. There is a great list of speakers on all quantum photonic directions. such as photon storage, quantum imaging, quantum sources computing, and so on. And with this, I would like to thank the funding, the students, and all my collaborators, and you for your attention. Thank you.
Thank you very much for the talk. And now it's time for questions.
I don't need the microphone. I have a general question to you. I remember once I attended a talk by John Martinis. He was working for Google already, and I was working in quantum photonics at the time. I remained impressed and depressed because we struggled to have single qubits while they were doing calculations, error corrections. They were suggesting so they have published things controversial, but my question to you is how photons and quantum photonics compares or can complement these advanced technologies. There's anything that superconducting qubits cannot do that need to be done with photons? Or
yeah. So I asked a very similar question to Professor Chirac some time ago, and he told me that in the end each platform is using benchmarks that are beneficial for their own platform. So sometimes it's a bit difficult to cross-compare different platforms, right? So something that I think it is clear, and is that I do not know exactly how the information from a superconducting system is going to be efficiently extracted and communicated. I know that there are people working on transducers that can do that efficiently and without altering the information that is within their millikelvin chip. But if you ask me, I think that at the moment the most promising platform for quantum computing is atoms, and this is what the group of Lukin is demonstrating at the moment, by far. And then it's going to be challenging for photonic platforms in order to compete with the numbers of atoms that they are using at the moment, but eventually those atoms will need to communicate with another entity, with another node, and for that you're going to need single photons or single photon structures that can partially or completely talk to other systems. So I don't know if this is more or less answering your question, but photons can propagate, and if you, to be honest with you, the 12 sources benchmark that is at the moment given by Quandela, if you were asking me 15 years ago that we would be at this level of technology evolution, I probably would have been much more negativistic than what we are right now. So these 12 photon sources probably is already within reach, either very, very soon or within the next decade. So we'll see.
More questions?
Thank you, Carlos. I'm going to ask about TMDs, of course. First of all, the wrinkles in the WSE2, you say the indistinguishability is quite bad, but do you think, I guess you're measuring where the wrinkles are, so there's no way of putting, so there is ways of putting wrinkles where you want wrinkles, or like using pyramids or structures or whatever. Do you think it's a way to go, or do you think that with the results that you have already on the random wrinkles, it's not looking too good?
I think that I'm not following that much. So I was participating on this result with the group of Christian at the time, and the conclusion that we arrived is that probably we'll have to have electronic contacts to try to deplete electronic states around the quantum dot and then have more coherence time for the single photon emission. Then about the wrinkle origin, in our case, it was formed by simply the position of the monolayer, and then when you remove the top part, that wrinkle is formed. I have been also participating in other experiments where we were generating this local strain by depositing the monolayer on nanopillars of, I don't know, like a few 300 nanometer tall and very, very small diameter as well, to imprint that tension close to the place of the nanopillar. And in that case, we were not able to characterize the indistinguishability, but I presume that it would be equally bad. What I said about the electronic noise, it's the most natural thing to me to assume, because TMDs by default are a surface material, so I guess that they can talk to many density of states of electrons in the surface. But I'm pretty sure that there will be other groups that soon will show better results, or even more interestingly, how in moire potentials you can have different emitters or two-level systems that can talk to each other and make interesting quantum states of light. But
thanks. Sorry, one more thing, because you already said something of the moire. You said you want to do heterobilayers of MOSE2, WSE2. Don't you think it's a bit too like, why don't you go for homo structures? Why not use WSE2 and just twist it? Won't it get like immediately very complicated with having the two materials there and then the combinations of the excitons and so on interlayer?
So for that end, we were thinking about trying to investigate what are the different mechanisms that rule the creation of this interlayer exciton. And we are thinking of using different types of excitation schemes for the intralayer exciton of the WSE2 and MOSE2. Different polarization, pulsed or continuous wave lasers, to try to understand a bit more about the physics of what is creating this interlayer exciton and how efficiently is created. Why homo or hetero? Probably there are very interesting things to explore. And if your group wants to collaborate for making the sample, I would be super happy to.
Of course, we can talk. Thank you very much.
More comments? More questions? Well,
I have been witnessing different discussions on the robustness of random numbers, random number generation. Do you think you have something to contribute in that area?
Yeah.
Intrinsic nature of.
Yes. To the best of my knowledge, with the single photon emission, you can also generate protocols for random number generation. I have been following some results in HBN defects where they are using the emission for that purpose. Although I'm not very sure of how do you make it, how do you benchmark it, and how good it has to be in order to be comparable with other very cheap ways of generating very good random numbers. Yeah, I think there is a company in Barcelona that are doing some chip that is using some nonlinearity of the semiconductor in order to generate this randomness. But I don't know, it would be interesting to try to investigate this aspect of random number generation also, because you don't need photons to be indistinguishable. You don't need to interfere anything with anything, so it would be perfect for the kind of emission that I've shown in HBN that is so distinguishable, right?
Okay, Carlos, thank you very much for approaching ICMM.
Thank you.